In this video, let's understand what is time complexity. Before understanding time complexity, let's understand what is real time, the actual execution time. In general, for example, I have algorithm A and algorithm B. So algorithm is just set of instructions to solve a problem, right? So to execute this algorithm A, it will take 10 seconds of time. To execute algorithm B, it will take 5 seconds of time. So we judge that, so it will take less time, 5 seconds. So algorithm B is faster than algorithm A. So here my point is we should not consider this real time, seconds or minutes, to judge which algorithm is faster. Because on two reasons we should not consider this real time. The conclusion is time complexity is not equal to real time. So real time means actual execution time, which is in minutes or seconds. Due to two factors, time complexity is not equal to actual time. The first reason is hardware, hardware of the computer, CPU and RAM. The next reason is programming languages and its compilers. See, this is one computer and its configuration is 2 GB RAM, i3 processor, and another computer 4 GB RAM, i5 processor. See, this the system has better configuration. So if you perform algorithm B here, for example, I have set of instructions like int I equal to 1 till I equal to 10, print values of I. So I will execute this algorithm in both machines. So of course, this system B will execute this algorithm in better way than the system which executes A, because it has better configuration. Of course, the runtime will be little speed in this machine. So machine to machine, due to hardware configuration, the real time we should not consider. That another reason is the programming languages and their compilers. For example, C++ is installed in this machine and Java is installed here. In C++, first code is converted to, in C++, code is directly converted to machine code. This will be executed directly. But in Java, the code is converted to bytecode first, then it will executed by the JVM. Here, this translation code to bytecode, it will be little overhead for Java compared to C++. That is why Java is slower than C++. Due to this translation code to bytecode, there is advantage for Java. It is platform independent. Okay, that is another point of discussion. For time being, the real time is influenced by hardware and programming languages. That is why we should not consider time complexity equal to real time. Then what is time complexity? The time complexity is how number of operations will grow or increases in algorithm as input size n increases. Let's understand this statement by taking an example. Here I'm drawing a graph. This is x-axis, this is y-axis. On x-axis I'm taking input size n. On y-axis number of operations. It is not time, it is number of operations. Here input size 5, 10, 15, 20, 5, 10, 15, 20. For example, I have an algorithm. This is example algorithm. For example, I'm taking n equal to 5 here. So when I take n equal to 5 here, the number of operations here, SOP statement will be executed till 1 to 4, right? So here number of operations are 4. It will be 4 operations. If I take n equal to 10, so till 1 to 9. So SOP will be executed 9 times. So total 9 operations. So this is X, number of operations are 5. If you draw these coordinates on this graph, n equal to 5 and y is 4 operations. So here 4 and x is 5. This, these two coordinates will meet here, and next coordinates equal to 10, y equal to 9. So these coordinates will meet here. So if you draw this graph, the curve will be in this way. And for example, I'm taking another algorithm. For this algorithm, I'm taking input n equal to 5 and n equal to 10. See, this is for loop is inside another for loop, right? So it is n operations, this is n operation. So we have to multiply 5 into 5, total 25 operations. Here 10 into 10, 100, total 100 operations. If you draw this graph, here the output is growing very fast. Here the output is growing. Here number of operations are growing very slow. That is why it is linear growth. Linear growth means the growth is little slow compared to this one. But here the growth is very rapid. If you draw this on graph, so it will be very rapid growth in the number of operations. So this is fast growing. This curve is slow growing. But in time complexity, we cannot tell this is fast growing, this is slow growing. We need some standard way to tell this. This is where notations comes in. We have three types of notations here: big O, omega, and third one is the theta. So let's understand these notations here. First notation is big omega. Its symbol is this. And next notation is big theta. Its symbol is theta. Next notation is big O. Its symbol is just O. Big omega used to express best case analysis. Best case, or it will be called as lower bound. Big theta, it is used to express average case of an algorithm. And big O, it will be used for worst case scenario. It will be called as upper bound as well. Let's understand all these three notations by taking one example. I have algorithm for linear search here. For example, this is linear search algorithm. The point of linear search is, for example, I have list of array here, list of elements in the array 37293. So if we give any target number, we have to find the target number. We have to return that index, right? So for example, first target is 3. If the given target as 3, target equal to 3, you will find this element in the first iteration. See here, the algorithm for linear search is iterating elements from this array and checking target. Target is equal to current element in the array. I'm returning that index, right? So first case, target equal to 3. So here the number of iterations, the number of operations just 1. Number of operations just 1. So we have to tell this is best case, right? So for best case, we have to use omega. Omega of 1. For example, if target equal to 2 here, so you can find it in the middle of the array here. So it is the average case. If target is 2 or 9, it is the average case. So the number of operations here 3. So we cannot write theta of 3, right? Theta used to describes average case, right? So we cannot write theta of 3 because we don't know in real time size of the array. That is why we have to write theta of n. Theta used to describes average case. And for example, target is 3. We have to iterate 5 times. So the number of operations are 5. For worst case, we have to use big O. Big O of n. These are standard way to tell time complexity of an algorithm in all three cases: best case, average case, worst case. This is correct way to tell this, but in general people use big O for all three cases. For here in this case, best case we used omega, right? But people use big O. For average case theta, but people will use big O for average case also. Of course, worst case we use big O. So people globally follow this standardization. Instead of using multiple notations, people use big O for all three cases. Even you can tell in this way. This is also correct way, but this is more precision way to tell this. The next concept is case analysis: best, average, and worst. So for given algorithm, we check in these three cases how it will behave in best case, how it will behave in average, and how it will perform in worst case. In this case analysis, we are more concerned about worst case because when we build software systems, we prepare for the worst case. For example, I'm building an e-commerce application here. So when we build e-commerce application, we don't expect just 100 users will access this application, right? So we expect 10 million people may access this application. We prepare for this worst case if 10 million people will hit request for this application. If our application is capable of dealing with 10 million users, this application even can deal with best and average. Here we are dealing with worst case. So dealing with best and average is easy, right? That is why here we are more concerned about worst case rather than best and average. Next concept is rules to calculate time complexity. First rule, ignore constants, ignore non-dominant terms, only consider dominant terms. See, for example, this is I have an algorithm here. Here loop inside loop. So this is n operations for given input. This is n operations for given input. Here we have three operations, right? First I plus j addition, then I'm adding it to sum, then I'm assigning it to sum. So here total three operations. It is loop inside loop. So the time complexity is 3n square. The exact number of operations for this loop 3n square. The next for loop, it is just n, right? It will perform n operations for given input. It is printing that I value. It is big of 1. So 1 into n plus n. This total is n, and next big of 1. So this is one operation. The exact number of operations for this algorithm is 3n square plus n plus 1. Here 3, 1 are constants. Here n is non-dominant term and n square is dominant term. So we ignore here constants and non-dominants. Here we ignore constants like 3, 1 and non-dominant terms like n. We only consider higher order terms like n square. Reason we ignore constants and non-dominant terms is, for example, this is the curve for the time complexity n square. N square means quadratic time complexity. So this is 3n, this time complexity is 3n square plus n plus 1, right? So it is more number of operations than n square does, because due to this multiplication and addition, this time complexity will have more number of operations than n square, right? So that is why the curve will be little more up. This time complexity is 3n square plus n plus 1. The next worst time complexity than n square is cubic time complexity. Think that n cube is worst time complexity than n square. And the better time complexity than n square is n log n, big of n log n. So here my point is, by adding these constants like 3 and lower order terms and constants, this curve, the difference between these two curves is just this multiplication 3. For example, it does 10 operations into 3, it is 30 operations will do this time complexity, but this curve will never come to this point. This multiplication and this addition will never add new powers to n square to reach here to here. To reach from n square to n cube, we need infinity number of operations as to be increased for the n square. So it will never happen infinity operations by adding these constants and lower order terms. That is why these are less important when we compare with number of operations infinity. This is the diagram I'm trying to draw there. So let me explain you here. So the difference between n square and n cube is infinity. To reach from here to here, we need infinity number of operations. These constants like 3 plus n plus 1 will never add infinity number of operations. Of course, there is slight difference between these two curves, but it is never equal to n cube time complexity. That is why we ignore these non-significant terms like constants and lower order terms. The next point is the current time complexity is n square. So to reach to its lowest time complexity, the gap between them 0. From current time complexity to upper time complexity, the gap is infinity. From here to here, the gap is 0. So these constants will never add power. Let me prove this difference is infinity, 0 and constant mathematically by using limits. See here I'm using limits. Here limit will help us to find how fn is behaving compared to g of n. Here fn we take one time complexity, g of n we take another time complexity which we want to compare against. For example, I want to compare these two. So take phi n square as f of n square as g of n. So this limit will help us how phi n square is behaving with the n square time complexity when n growing to infinity. So this is the use of infinity with the limits. So f of n one time complexity and g of n is another time complexity. So by using this limit, we can find that is f of n growing slower or faster or same way. In the same growth, fn is growing with the g of n. This we can find out by using this limit. Here, first I'm trying to prove this infinity here. So the infinity is the difference between n square and n cube, right? So here I'm taking f of n as n cube, g of n as n square. So the result should be infinity, right? F of n, g of n, n cube, n square. So if you cancel n square out of n3, the result is n. If you substitute n with the infinity, so this n will become infinity. Difference between these two time complexities, infinity number of operations. Okay, so this one is completed. So as result is infinity, it means that f of n means n cube is grows faster than g of n, faster than n square. So f of n cube belongs to other time complexity class. It is higher time complexity class. As a result is infinity. The next I'm trying to prove here is the difference between n square and n log n is 0. I'm taking n log n as f of n, g of n as n square. Here n I'm cancelling one time here, n log n by n. So when I substitute n with the infinity, log of infinity infinity. So anything by infinity is 0. Since the result is 0, f of n grows slower than g of n. So here n log n growing very slowly compared to n square. So this n log n belongs to lower time complexity class. That is why I declared it as a n log n time complexity, this curve. So the next comparison is this constant phi. I'm taking example time complexity as here phi n square plus 2n. So this has f of n, and next one is the g of n. F of n, g of n. Here one time, here two times n square. So the result is 2 by n. Anything by phi plus 2 by infinity. Anything by infinity is 0, right? So the result is phi here. So the difference between these two curves is just constant. Here infinity means the difference between n square and n cube time complexities. For n square, whatever the constants you multiplied with n square, it will never reach to n cube because the gap between our number of operations difference is infinity. The next phi n square, see phi n square will have more number of operations than n square, but it doesn't mean that as many as operations as n cube does. This is very important point. Here phi n square, if you consider phi n square or some other constant 3n square, 2n square, if you consider every separate every time complexity as separate complexity class, it is very difficult to define every possible constant factor with different complexity category. For example, tomorrow 2n square, 3n square, 5n square, 6n square, every constant with some time complexity we cannot define a separate time complexity category, right? So it will be very impractical. So this would make complexity analysis impractical because actual order or growth remains same. Here the actual growth is same between these two. This constant factor, it is very minimal compared to infinity. That is why the growth rate between these two is same. Here, growth rate means they comes under same time complexity. That is why we group all functions with the same fundamental growth into single class. That is why this all comes under n square time complexity. Functions with the same dominant term belongs to same complexity class.